Okay, so today's main topic is indexing, but when we talk about indexing, we generally talk about B-tree indexing. So many databases will implement different types of indices, and they are becoming more and more important depending on what type of data you want to store. But B-trees are so efficient that we always first learn B-trees, and then we will learn other variations of them and things that are completely different and why we should care about them. Okay, so B-tree indices are very similar to some of the data structures that you studied, except that they are disk-bound. So whatever you study in data structures is basically for data that you have in your own computer's memory, right? So everything fits in memory, and then you figure out how to organize it so that it's efficient to search. But those data structures are generally not very good for disk-bound data because a disk page is generally fairly large that you can put a lot of stuff in it. So, for example, one of the basic things you learn in, I assume, data structures is binary search trees, right? Have you seen binary search trees? Okay, so binary search trees are basically nodes. All right. So if you are looking at, for example, a binary search tree, so you have a node, and how many pointers there are? 2, right? So you have a pointer left and a pointer right. And then you have basically some key value that tells you whether to go to left or right, right? So that's basically the idea of a binary search tree. So let's say 20, okay? So generally that means that if you are searching for a value less than 20, go to left, greater than or equal to 20, go to right. Okay? So far so good? But the point is that a binary search tree is not very efficient for a database because what I want to do is create an index such that each node in the index, a node of index, is the same as a disk page. Basically, I want to store a node into a disk page, and I want to read, when I read, remember the one thing that we should have learned from last time was that when you read data, the smallest unit you can read is a disk page. So when I read a disk page, I want to get as much information as possible. And taking a binary search tree and storing it in a disk page would not be very useful because it's a very small amount of data, 2 pointers and 1 value, right? So this is not a lot. Believe it or not, lots and lots of people tried very hard to take a binary search tree and pack it into nodes, but that turns out to be a very difficult thing on itself. Instead, I am going to do not a binary search tree, but an n-ary search tree. Instead of 2 things, I'm going to have n things. So think of it like this. So I'm going to have a node with n key values. And n plus 1 pointers. Okay. I will give you an example in a second. But a B tree is basically a binary tree, but not for 2, but it's an n-ary tree for some n. And the n may vary depending on what you index. So if you're indexing large values, like big, long strings, then you may not be able to put a lot of things on a disk page, but likely you will still be able to put more than 2. But generally, n tends to be kind of large because your disk pages are fairly sizable. For example, on my Mac, I didn't check this one, but on my other Mac, a disk page is about, for example, 4K. So I want to basically figure out how many things I can fit in a single disk page, and that will determine what my n is, right? So if I have a single integer that I'm indexing as a key value, n will be large. If I'm indexing a 20-byte string, then it's going to be long because I can stock fewer of those in a disk page. Okay, so a binary search tree is, a B tree is like a binary search tree, but it has n. The other thing that is different is that often a B tree is basically a search tree that tells you where tuples are stored. So it doesn't actually store tuples, it doesn't store data, it tells you where data is stored. So basically leaf nodes contain pointers to data pages. Okay. Because when we talk about indices, we generally think of indices as a secondary access structure, meaning that data is stored on data pages, and then I'm building a secondary lookup with the B tree. So because of that, leaf nodes don't contain the tuples themselves, but it contains pointers to tuples. Okay? So this is not always true. For a moment, just forget that there is another, possibility. So we are going to just stick with this and then see how to waive this one. So because they are secondary storage. So basically what you would do is you would basically say, create table XYZ. Okay, you create a table that basically will store the data tuples wherever they are. Then you create an index on some attribute of that table, which is a secondary data structure. So you would generally say create index ABC or XYZ IDX1 on XYZ of ID. Okay, so the primary is basically however this table is stored, often in no particular order, which has a name in databases, they call it a heap. It just says that you basically put the tuples in the order they arrive, and then if you delete tuples, you put a tombstone that was deleted there, and eventually you can clean up. There's a vacuum operation, you can clean up and clear those. But data is stored wherever it is stored. And then, so this is, the data pages go where this one is stored. And then you have index pages that store pointers to those pages. So remember we talked about how your data tables have tuple IDs. Tuple IDs, actually tuples have a physical address telling me what specific data page contains them. But in reality, those are changed to tuple IDs that are logical, 1, 2, 3, 4, and then those tuple IDs basically are stored in here so I can find which tuple is there. Okay? And there's kind of a rough approximation of this in the data that I will give you, depending on how lazy I am. I was kind of lazy, so I didn't actually do the division prop points very well, so I will try to fix that by tonight. Okay, so let's see a basic few rules, and then we will see some examples of what the B trees look like. So generally speaking, we use the term B trees, but in other books, these are actually called B plus trees. So B plus trees actually are the correct name for what we are going to talk about, but very few places where you will find implementation of B trees but not B plus trees, so that's why we use them both. But technically, a B tree stores actual tuples at the leaf level, and a B plus tree stores pointers to tuples, but our book doesn't distinguish, so we will not distinguish. So basically, each B tree has a capacity called n. So n basically tells you what is the maximum you can store in a node. So this is the max that can be stored in a node. And I cannot put more than n just because that's the physical size of a disk page. But I also want to make sure that no disk page is very, very empty, because then I'm wasting a lot of space. Because if I'm wasting a space, then my index is very large, then it defeats the purpose of having an index that has capacity n. So basically, each node is a disk page. And all nodes have at most n key values. And n plus 1 pointers. Okay. And all nodes except for root have at least n over 2 key values. Okay. So that means that is n over 2 plus 1 pointers. Okay. The only exception we said is the root. And the point is that basically I will try to pack as much information as I can onto each disk node. And so no disk node should be empty. In general, you can put no more than n things. In practice, you will probably put about 70% of n, just so that there is room to grow as well. So you will not actually try to pack it so tightly that as soon as you insert something, there is no more space, you have to split. So in practice, you actually keep them about some percentage full. But maximum is n, minimum is n over 2. The only exception is root, because if you put things and eventually your tree splits, you will have a root with only 2 entries. So in that case, you cannot have this rule for the root. The root can have fewer. So root can have 2 pointers and 1 key value. Okay. B trees are balanced, meaning that the path of all, the length of all paths from root to leaf are of the same length. So they are balanced trees. And we talked about how leaf nodes point to tuples, and internal nodes point to index pages at level below. Okay. So these are the main properties of a B tree. And we will basically maintain all these for every single operation that we do. We are going to make sure that the trees remains balanced, that nodes have between n or n over 2. And the leaf nodes will point to the tuples. And I guess I have one final thing. Each leaf node has a pointer to the next node. So it's called a sibling node. All right, so n is typically large. I've actually looked at, for example, for the real data for IMDb, it's like, for example, for the actor ID, it's going to be something like 360 entries per node. For movie rolls, the one that you're going to use is about 40. So, you know, the n is somewhere around hundreds generally, right? So generally you can pack a lot of information in a disk node. But when we give examples, we are going to use n equals 2 or n equals 4 just because I cannot draw too much. Okay? So for us to be able to see things, I'm going to use small numbers of n, but typically n is very large. Okay? So let's try to see an example. So this is where having this tiny paper is the worst, but I will try to do my best. So let's say n is equal to 4. Okay? So that means maximum is 4, max is 4, and min is 2, right? So all nodes should have at least 2 things and at most 4 things. So suppose I am indexing a table, and we have, you know, so let's say table T. So I have T1, and T has A and other attributes, but I'm going to only do A. So T1 has A of 1, T2 has 3, T3 has 12, T4 has 18, T5 has 4, T6 has 8, etc., etc., right? So each Ti is basically the address of that tuple. The address of a tuple basically tells you which disk page that tuple is in, and within the disk page, which the offset that this tuple is stored in. Okay, it's a pointer to an actual disk page. Okay, so when I construct my B tree, I'm going to basically point to these tuples in the leaf node. So the leaf nodes, think of them as the following. We said n is 4, so I can store up to 4 tuples, right? So, for example, if I store tuple 1, for tuple 1, the a value was 1, and this is going to be a pointer to tuple 1. The second one was 3, then I'm going to have a pointer to T2, and this was, let's say the next one is 4, this is T3, okay? So obviously so this is an index on T of A. So I will find all the values for A, and I will sort those values. It's going to be in the sorted order, and I'm going to put it at the leaf level, okay? And for the sake of argument, I am not going to fill every single node, so we can see this. And we said that we actually have, if I have 4 maximum, so I have 4 key values, but 5 pointers. So at the leaf level, this is a pointer to this tuple, this is a pointer to this tuple, this is a pointer to this tuple. There is nothing here, so this is empty, right? I actually have a free space here in that node. And this is a pointer to the next node in the leaf level. So this is going to be a pointer to the sibling node. So like this. I'm already running out of space. Something like this, right? So in this case, I have 4 nodes in the leaf level, right? And each node points to the next leaf node. And I'm going to put some more values here. I have 8 and 12. So this is T6, this is T3, and I'm going to make up some more random areas, T18, 21, 23, 25, 24, and 30. And these will all be pointers to the appropriate tuples. Okay. So this is the leaf of my B tree. So basically, I took the information for whatever I'm indexing. So the key value is A. I found all unique values of A. I sorted them. I packed them into nodes. Each node has the key value and a pointer to the tuple, and then a pointer to the next. And this one, obviously, there is no other one, so it points to nothing. Now I'm going to build a sparse index on top of this. So on the upper level, my indices are going to basically point to these, and I'm going to draw them a little differently. So I'm going to have 1, 2, 3, 4 key values, and 1, 2, 3, 4, 5 pointers. Okay. So I'm going to point basically to this node and to this node. And I'm going to point to this node and this node. So the internal nodes also have at most 4 key values, but 5 pointers. And what they will do is they will point to the division point between these two, left and right. So for example, these 2 pointers, I need to put the key value that distinguishes between these 2 nodes. What's the value that distinguishes between them? Remember, go to left, go to right. What value can I use? This is an 8. 8. Or 4, right? One of the two. Either the biggest value here or the smallest value here. I'm going to use the smallest value here. Though in the homework, I actually did the other one because that was easier. That's the laziness. Okay. And then in here, what will I put for this one? What is the key value that distinguishes between these two? 24. Now, in this index, I'm assuming that there are no duplicate values. We will talk about what happens if you have duplicate values. Okay? So, and I can put one more. One more level above this. Now, at this level, I want to write the key value that distinguishes this subtree from this subtree, which is what? So what is the point that if it is less than that, go to this whole left subtree? Between these two is 24. Between these two is 8. Between this two is 18, right? So if I'm searching for a value less than 18, I need to definitely go down here. And then if it is less than 18 but greater than or equal to 8, I go to this side. If it is greater than 18 but less than 24, I go down here. If it is greater than 18, greater than or equal to 24, I go down here, right? Depending on how you constructed your tree, your search algorithm adapts to this. Yes?
Is that 25 plus beta?
This one?
No.
Oh, this one, yeah, that makes no sense. So let's say that is, just make this 22 and make this 23. Thank you. Yeah, that makes no sense. Okay? So this is the general idea of a B tree. But now consider this, instead of 4 values, you can have as many as hundreds of values, right? So instead of doing a 2 decision, you actually have to scan in the range of values what is the right pointer to follow. So putting this aside for 1 second, let us try to think about, for example, what would happen right? We just saw an example that was very, very empty, but you could actually have a lot more going on. And then you have to assume that there are leaf nodes at all of these. Okay, so let's say you have 20 and 50. So that means if it's less than 20, you have to follow this node. And in here, if it is less than 10, you follow this node. If it is less than 15 but greater than or equal to 20, between these two, you follow this node. If it is less than 20, so if it's less than 20 but greater than or equal to 15, you follow this node, right? So if it is greater than 20, greater than or equal to 20 but less than 50, you follow this node. Then here, for example, you can have 25, 30, and 40. I don't need this one. Okay. And then greater than 50, you can have 60 and 70. Okay. One of the things you note is that you only need 2 key values if you have 3 pointers, right? Because for each pointer, you basically have less than go here, right? More than go here. So for example, this pointer here points to what? So you have, if you follow this node, you've come here because it's greater than or equal to 20 and less than 50. So now you've come here, you know that it is greater than or equal to 25 but less than 30, right? So this node will contain 25 inclusive up to 30 values, for example. Any questions so far? So basically, since I am able to make many decisions at each node, this is very efficient because my trees are going to be very shallow. So search is very simple. Oh, here's some cleaner ways to look at this. I actually had better ones, but so this is kind of the cleaner values. I have not yet put them online, but I will. All right? This is the same information, but somewhat cleaner, so you can see what's going on. Okay. So if I'm searching in the index, that's interesting. Okay, given key value A is equal to X, start at root, find the first pointer such that, so you have to try to find the first pointer that is less than or equal to X, greater than or equal to X, right? Such that first pointer that is greater than X, and follow the first key value. Follows the pointer just before this key value. Okay. And you will continue repeating this repeat until leaf node is reached. Once you have reached the leaf node, then find the key value if it exists in the index, right? Find if leaf node contains the key value X. If not, return empty. Okay. If it does contain, then find the tuple ID. Find and return the tuple ID. depending on what your query is, if you need to actually find, for example, the name of, not the ID, you were searching for A, but you need name, then you need to go and read the data pages for that. Okay? Now, the nice thing about B-trees is that while they are very useful for searching for equality, they're also very useful for searching a whole range of things. That's why they are so popular. Okay? So, search for range. So this was search for equality. Okay? So now I'm looking for not A is equal to X, but I'm searching for X1 less than or equal to A less than or equal to X2. Okay, and you can see versions of this. So now I'm not searching for a single value, I'm searching for a range of values. But actually this algorithm is not so different. What I'm going to do is add a small thing. So I'm going to find the first value greater than or equal to x1. Okay, and I'm going to follow this until I find the leaf node. Okay, and then I'm going to repeat until leaf nodes contain values greater than x2. Find all entries in leaf node in the given range, and then retrieve the next leaf node using the sibling pointer, and continue. Right? So now if you're doing a range search, the same thing is true, except you have to first find the first node in your range. So for example, if I'm searching between 40 and 60, first I need to find 40. So I'm going to go left of this, right of this, and I'm going to start with this one, 41, then follow the leaf pointer, find that I have found a node that is greater than 60. I know that I don't need to read the next one because it's sorted, then I will stop. So because of that, I never have to go back to the upper levels. I can just continue scanning at the leaf nodes. I can do these range searches very efficiently. Now, if you've been following and paying attention to what I said last time, which I understand was very, snooze-worthy, but it is important. This is very optimized for magnetic disks. So what I will generally do is put this leaf node in basically consecutively, either on the same track or on the same cylinder. So it's actually very efficient to scan this leaf node, right? Generally, I can just patch these pages very quickly with a single seek, okay? So index scan can be very good if this is actually well maintained. So this is one of the reasons not only this is optimal, but it's also very fast to scan in the leaf node. Any questions so far? But wait, yes.
So what in that situation, what is the performance benefit of not scanning? So of following the B tree?
Well, if you only know that you have only one answer, right, then you don't need to scan. But if you have multiple answers and your index is actually sorted by that, then you will for sure scan.
Let's say you only have one answer. How much of this speed up do you get?
Well, you don't need then to read. Well, if you have one answer, why would you scan it?
Well, because presumably there's seek time to consider. Maybe
Yeah, but you well, okay. There's different answers to that. So suppose you've come to the leaf node, right? And if you only need that leaf node, you're done, right? There's no point to scanning the rest. It's true, you're already at that track. Why not scan some more? But there are lots of algorithms that do prefetching.
I guess we're I guess it doesn't really work because you have to find the leaf node to begin with, but if for some reason never mind.
It's gonna come why you might do that. Okay, so so let's say that you are not indexing something that is unique, but it can actually have duplicate value. So it may turn out, if you're storing on, let's say, the primary key, that there's going to be only one value for each primary key. Your Postgres will create an index for you regardless. This is like by default, it is so useful. But if it's a value that is not unique, then you are not going to have one tuple per value. These values will actually repeat. In that case, you're going to create a slightly different index. It will look something like this. And God, I hope that I created this correctly for the homework. But it will look something like this. This is what I've been working on the whole weekend. All right. So you can have duplicate values at the leaf node, right? So that means, for example, there are 3 tuples with value 15, 2 tuples with 18, many tuples with 41. And however they are stored at the leaf node. But there is no need for you to really point to every single one of them in the higher level, right? So you only need to really care about what is the new novel information, right? Because the idea here is that it says that if you're looking for something less than 11, you have to go to the left. If you're looking for something greater than 11 or equal to, you go here. But this node starts with 15, but if I were to put 15 here, it will say go to here for 15. But that's not useful because if I'm looking for 15, I should start here. So what I will put here is actually the first node, the first value that is not repeating, right? So since 15 is repeating, I will have the first value here that is not repeating. So this way, you're actually going to be able to go, if it is less than 18, you're going to go here, and then you have to scan in the same way we were talking about until you find a value that is not 15. And same as here. For example, here, if it is greater than 22, then you're going to go here. And here, if it is greater than 22 but less than 55, you're going to go here. I don't want to use 18 because 18 is repeating here. 22 already is guaranteed here. And I don't want to use 41. I guess I can use 41. I don't know. I don't remember why I have 41. I think I can have 41 here, but I don't want to have 41 for this one. And for this one, it's 55. Only if it is greater than or equal to 55, you go here. If it is less than, like 41, you go down here. I think I should have 41 here. It's a little tricky. It's been a while since I did this. Okay, so if you have duplicate values, there's a slightly different algorithm. I think that I'm not doing this correctly in the homework too. But regardless, it'll be fixed by the time I post this. So basically, you only want to put the values that will point to the left and right in the correct way. But you will be given the B tree, luckily. You only have to search. It's for me to get, sweat this one up. Okay? So, yes? If I put 41, yes, that's true, right? I cannot go here, so I cannot put anything here. So basically, what I'm telling here is that if it is less than 55, you always go here, right? There is nothing to go here for. I don't actually even need this necessarily. And if it's greater than 55, you go here, right? Because if you're searching for 41, you still have to go here, right? So there is no decision point here. I think that's what I was trying to get at. This is kind of tricky. All right. Now that this is so tricky, what happens is that B-trees are actually extremely useful for indexing on more than one attribute. You don't have to just index on ID. You can actually index on multiple attributes. So this was an index on a single attribute, let's say A. Well, you can actually index on multiple attributes. Such as A and B. Okay? So in this case, things are a little bit more interesting. And we will do various combinations of this. But I just want to start you off, and then we will do this after a short break. So if you have multiple attributes, you basically have now two things that you sort by. So you sort tuples first by A and then by B, right? So you have two sortings, right? So for example, if you, hey, not that. If I have actor ID, movie ID from movie roles, order by actor ID, movie ID, right? So if I actually create an index on actor ID first and movie ID second, right? So what I will have is, I will first have tuples for all the same actor, then all the movies for that same actor. So actor 1 has 3 movies, actor 2 has 1. If you go down here, actor 8 has many movies, right? So you basically sort by the first one and sort by the second one. So whenever I create an index, it's going to be sorted by first the first value and then the second value. That means now I can search for these two in various different ways. So basically, now I can ask queries such as A is equal to B, A is equal to X, and let's say B is between Y1 and Y2. You will not write it like this in SQL, but I'm just showing you an example. You can search for X1 and X2. And many other variations of this exist. Okay, so we will talk a little bit about what are all the different algorithms for these. And this is what you are expected to do for your homework. Right? So implement one algorithm that will do all of these. So let's give a short break, and then I will talk about search algorithms for these, and then we will talk a little bit about insertion and other things.